All right, here, I hope you do remember after this long weekend what we were dealing with. We started studying exponential functions, and we figured out that the derivative, if it exists, is of the following form. So if I'm trying to take the derivative of a to the x, I use that second notation for differentiation, because I can then use the this sum of powers to product. Yes, then I factor a to the x from this limit, and I obtain limit as h goes to 0 of a to the 0 plus h minus a to the 0 over h. You understand? And even though the limit that I obtain is still a complicated limit, I do not know how to solve it, I notice that this function has an interesting type of derivative. If you start calculating the derivative at any point, the result ends up the same as if you actually calculate it at 0 and then multiply by the function. So the derivative looks essentially like the function if it exists, right? So if this expression here, this limit exists, it will be some number, and this number is the derivative at 0. So do you see what happens here? The function is not very much changed by calculating the derivative. Now, we can cheat a little bit. We can, instead of calculating exactly as limit goes to 0, as h goes to 0, I can try plugging in very small values of h, because what is the limit here? The limit means that as you observe that h in this expression is a small number, smaller and smaller, then you will observe that this limit will converge if it exists. It will be some number. So then I can hope to observe what that number might be by plugging in small values. So I decided to plug in 0.001. So I plug in 1 over 1,000, considering this to be a small number. And when I plug it instead of the h, I get a number that looks like 0.693. You can try in your calculator and plug in even smaller numbers, and you will see 0.69 and something else. So you expect it to be some number of this form. If you do the same thing for 3 to the x, and then the number you obtain is actually slightly bigger than 1. So guys, before I continue, is this idea for now, is it clear? Is it clear what we have attempted to do? Okay, good. Make sure that, let me know, guys, so I can continue onwards if it's clear. All right. Silence your mics, guys, if you are not saying anything. So here is my my question, right? So when I have this expression, right? So I have the derivative of a function is the function times its derivative at 0. What's the best derivative for 0 I may hope for? In other words, where it's as simple as possible. What do you think? Thank you, Christian. And the rest of you guys, what do you think? The function multiplied by its derivative at 0, what's the simplest derivative at 0 you may hope for? Two people say something. What about the rest of you? Okay, 3 people, 4 people. Well, may I ask you this? Christian, okay, here you go. And now you ask, or 0, right? 0 might even be better, correct? than 1. I mean, 0 means whoop, it's all gone. The function multiplied by 0 will be identically 0. Why may we not hope to get derivative 0 at 0 for this particular function? You understand what I mean by hope, guys, right? So in essence, you will see already today that we often want to take more than one derivative. We want to take derivative again and again and again and again. And if you take the derivative again and again, then it matters what you multiply the function by, because you actually have to carry out that that calculation. So Dragon says 0 can't be in the denominator. That it's true, we don't want 0 in the denominator, but why does it mean we cannot get derivative equal to 0? It has nothing to do with the denominator. Guys, you understand my question, right? So this is the first function where it's not like what we did before. You actually have to be rather clever. It's an entirely different mode of thinking that you have to adopt. So my question is this, guys. So a few of you said zeros. Well, 0 in the denominator. No, why can't we hope to multiply by 0? So guys, very important. Do you understand how we obtained this pattern? Like it's just a pattern. I haven't bothered verifying that this limit exists. So Alexa says 0.001. So Alexa is actually, you're saying quite an interesting idea. So she's saying you can get close to 0. Maybe what you're meaning, Alexa, is that you can get closer and closer to 0. But can you actually get a 0? Closer and closer to 0, yes. If you take numbers like 1/2, 1/3, 1/10, the derivative in your calculator, you can play around with it, will be closer and closer to 0. But can we actually get 0? Why can't I get 0? One moment, guys. There is some sort of no. Ah, here it is. Yes. Okay. All right. Why can't you get 0? Well, careful, Alexa. H approaches 0, so right. Do you understand what is that 0 that I'm talking about? Here, okay. Look at it carefully, guys. Right. You see that if I have an exponential function, its derivative will be the derivative at 0 times the function. Yes. Times the function. Now, if I get the derivative at 0 equal to 0, then the derivative of the entire thing equals to 0, of the entire function. What graph will it have if its derivative is 0? That's my question. If I take the derivative of a function and I find that everywhere it's 0, you see, because in here, if I find it 0, the derivative is 0 at 0, then I found it's 0 everywhere. You understand? Because it's the derivative of the function at 0 multiplied by the full function. If that full derivative is 0, the entire function is identically, the derivative of the entire function is identically 0. That means that the function has a graph that looks like a what? Beautiful, Alexa. Horizontal line, not just a line, but horizontal. If you find, guys, do you picture it? The derivative in Calc 1 is just referring to the slope. So if you find, let's say that, let me ask you this question, guys. If you find that the derivative everywhere is equal to 1, right? What is the graph of the curve that I took derivative for? What is the graph of the curve I took derivative for? Can you see it? What will that be? The derivative everywhere is equal to 1. The graph is what? everywhere. So I'm not talking about this problem in general. I found the derivative of some function everywhere. The derivative when I look is just equal to 1. Equal to 1. David, or you see, it's a different question. I'm just testing your ability to put the information together. So it's entirely different problem. Okay. So for a moment, I hope it's not confusing you guys. I'm asking you this, right? So we don't know what section we are in. We just wake up and we found that the derivative of some function everywhere is equal to 1. Nothing to do with this problem, okay? Everywhere equal to 1. What graph does it have? Lakey, very good. Do you understand what it means, guys? Everywhere 1, it means everywhere you zoom in, you're seeing a line, and all the lines have slope equal to 1. The graph, the picture of a graph that you have, from the derivative is just lots of line segments. It's a chain of line segments attached to one another. If everywhere the line segments have slope 1, that means the line segments are aligned, right? So in general, when you zoom in at different locations in the curve, you have sometimes this is the line, sometimes this is the line. So you have in general just this type of pattern, right? You have this type of pattern, right? So you think, here is a line, here is another line, here is another line, here is another line, here is another line. They're just microscopic line segments attached to one another, yes? And the slope here will be something, here it will be something else, here it will be something else, here it will be something else, right? So the idea is that a curve, any complicated curve that's differentiable is just a chain of microscopic line segments. Really more microscopic, because as you zoom in, you will see possibly more difference, right? As you zoom in, you see that there are always more line segments. Good. So I hope you understand, guys. Very important idea here. Yes. So we know that it's an exponential function. Exponential function cannot have derivative equal to 0. How do I know that? Because let's say take 2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. It's not constant, right? So if it's not constant, it could not be that globally the graph of this function is a horizontal line, which means that the global derivative cannot everywhere equal to 0, because that implies it's a horizontal line. Good. So you understand what is this one that we have here? It's just the derivative at 0 can equal to some number. It's just in this case, the derivative at 0 multiplies the full function. So that derivative cannot possibly be equal to 0, because that will force the global derivative at any x to equal to 0. Yes, but we can hope to get 1, right? We do hope that there will be a limit for which there will be some a for which the limit is 1, because then the derivative of the function is the derivative at 0 times the function, which will be 1 times the function, and it ends up being the function, the original function. You understand? And then the derivative is particularly simple. You can take, let's say, 2 derivatives. It just first derivative, it's the function. Second derivative, it's the same function. On the other hand, if you have, let's say, the f prime of 0 equal to 0 to the power 0.69 or something, and then every time you take the derivative, you multiply an extra time by 0.69, and multiplying many times by 0.69 isn't simple. You understand? Because multiplication isn't such a simple operation. Think about it. Calculate 0.69 squared without a calculator. Do that for a cube for the degree 4 and onwards, right? You will tire very fast if you actually have to carry that calculation. But you will never tire if I tell you calculate 1,000,000 derivatives of a function where the 0 derivative is 1. You will never tire. You right away know the answer. You follow? Let me just write it again, just to be sure, guys. All right. So if I were to take, let's say, 100 derivatives of 2 to the x, I will roughly get, it's actually already going to be very much an error, because the more the more numbers you have, the more you might be worried there is more of an error, right? Even though of course it's driven to 0. So that would be 0.69 roughly to the power of 100 that you have to calculate times 2 to the x. You understand? That's from the constant rule. Everybody understands how I get this formula, guys? Let me know before I move on. And do that fast if you could, please. Two people. What about the rest of you? You understand? Every time I take the derivative, a constant drops in, and derivative can move across the constant. Right? We have that if I have a constant times a function and I take the derivative, that just ends up being constant times the derivative of the function. That's what I'm using here, right? So I took derivative 1, so I just then move across the 0.69 and then another one drops. That's the idea. Good? Today I need you to be very sharp. Very sharp, guys. And if anything is ever unclear, resist this urge to go home and forget about it. Stay after class. We can discuss at your terms. We can achieve so many beautiful things if you, of course, allow me to do that. So here is our hypothesis. This is where we ended up in the last section. Our hypothesis is that there exists some number which I call E, and the number by experiment is between 2 and 3, where the limit as h goes to 0 of e to the h minus 1 over h equals to 1, because that limit is the derivative of e to the x at 0, right? So I just have to find that number, and I think it might be between 2 and 3, and that's what I do, okay? So here are the two important comments that I should make, is that when I observe that 2 to the h minus 1 over h is approximately 0.693, and I did the same, I did the observation that the limit as h goes to 3 of 0 as 3h minus 1 over h is 1.099. I made assumptions. One assumption is that the limit exists, because I mean, I just estimated it at some number. Maybe I will see a very terrible behavior past 1 over 1,000. Maybe it will be starting from 1 over 1,000,000 that I see some deviant behavior. Okay, that's one comment. But the thing is, the other part is that you used your calculator. How was your calculator able to carry out this calculation? If you do not know that, then you know it's just the same as just believing in something, right? Because your calculator, what procedure does it do? You when you take 2 to the power of 0.001, you are taking the 1,000th root of 2. Can you even take the second root of 2, the square root of 2? If you do not know a procedure to calculate it without a machine telling you the answer, then what you did is in some sense meaningless. And calculators were not available when those discoveries were made. They came way before calculators, right? So those are the questions that you have to keep in mind. So here is something that's pretty interesting, right? So in mathematics, that's really true, right? You can give arguments like that. Why does Santa Claus exist? It's because you believe in Santa Claus. The existence is a consequence, a direct consequence of your belief. And I will show you how that works, okay? So what are we truly trying to figure out? We're trying to find a function whose derivative equals to the same function. A function whose derivative is that same function. We were inspired by considering exponentials, right? I didn't have to solve it to realize that if I'm armed with exponential laws, if I believe that they hold, I see this limit, right? I see that when I take the derivative of any exponential, it's the exponential multiplied by its derivative at 0. And then I hope that this derivative at 0 equals to 1. So I'm in essence searching for functions whose derivative equals to the function originally, and the value at 0 equals to 1. That's because we know that exponential to the power of 0 equals to 1. Remember how we figured that out, guys? Do you remember? It's very simply is that when you have powers, remember when you have, for example, 2 to the power of 3. That just means 2 times 2 times 2, right? That's where we have this notation. It's just we begin by mimicking multiplication. Now, if you have, let's say, 2 to the power of 3 divided by 2 to the power of 4, what is that? That is simply, you can imagine the notation that you can use is just 2 to the power of 3 minus 4, yes, which is 2 to the power of minus 1, and that just means that 2 survived in the denominator. It's just a way of bookkeeping. You understand? It's a code. 2 to the power of minus 1 means that some operation was carried around and 2 survived in the denominator. That's why this law is not arbitrary. You're trying to make the algebra of the powers work for all values. Make sense? I skipped already one thing. Is, remember, if you have 2 to the power of 3 times 2 to the power of 4, you just end up observing that you multiply 2 by itself 7 times, or 2 to the power of 3 plus 4. Good? I hope that's, guys, you see, one reason that we are slow is because I try to make this class self-sufficient. I review material that you are supposed to know in theory before taking this class. In practice, I notice people don't know it, not just I. I actually spoke with my chef, my boss, right? And you understand the failure rate for calculus, typical failure rate, is 50%. He showed me the exams. My God, 50% of people. It's not happening with me, but it's not because I'm such a great teacher. It's because I don't grade you so harshly, right? I mean, really, it's actually far worse. Understand? If I were grading based on just completely the value of the student, how the student understands, it will be probably 20% that survive this course. You have to take that into account. I want you to do more, to actually catch up. Okay. So anyhow. So in much of the review, guys, I can do if you stay with me after class. We can make this class self-sufficient. It's just the problem is the semester is shorter than it should be by far. So we pay for that once the semester is over. I try to build up your base. Good. So do you understand why 2 to the power of 0 is 1? It's because 2 to the power of 0 means that there was a combat between the numerator 2's and the denominator 2's, and they were all cancelled out. You understand? That's why we say 2 to the power of 0 is 1. It's just a nice code, because it's 2 to the power of 3 minus 3 means we have equal match. Denominator 2's and numerator 2's. Good? So because of that, look at it, guys. F prime of x is f of x. F of 0 is 1. We're guided by, we're just thinking, okay, those are the conditions we want. It's called the differential equation. In other words, find me a function that does not change under derivative and such that at 0 it equals to 1. Because e to the 0 we think is equal to 1. You understand? That those are the conditions that we make. But we don't know anything about e to the x. If you understand the more abstract point of view, we're just guided by those two conditions. We don't know if it has to be exponential or not. We just ask, derivative of the function is the function itself, and at 0 we want it to be equal to 1. Okay? And then the question is, what will we produce? So here is my first and very important question. If you understood what this entire discussion about polynomials, and think about it, and don't be worried, guys. I want you to tell me not what you hope I will hear, but what you truly think about. So could the function that satisfies this differential equation be a polynomial? That's my question. Could it be a polynomial? Could, in fact, e to the power of x be a polynomial? Do you understand my question? Okay, so would anybody like to tell me what is it that I'm asking in much simpler terms? Polynomial is just this very lofty word, but what am I truly asking? Okay. You see, Alexa, so you say when you input a number in e to the x, does something different come out? It's vague what you're saying, right? So when you think about it, thank you for writing, by the way, but think, does it make, is what one says vague or not? And try to then make it clear. Something different, different means different from something else. And who says e to the x is just e to times e? Careful, who, right? E to the x means e to some power. Interesting. If you haven't given me your birthday, don't forget to do that, guys. So you don't remember what I'm asking. Let's see again. What is a polynomial? Thank you, Stephen. That's precisely right. Right? I would not use the word satisfied, but aside from that, excellent. Could I express the entire machinery of this function? In other words, could I make calculations only using addition and multiplication? That's the question, right? Now it's think about e to the x. Does it only involve multiplication and addition? In other words, when you say addition and multiplication, you are allowed not to use any of those operations. You understand? You have only, you have two buttons. You have the button to multiply, and you have the button to add. You also have the bottom to write, let's say -2, right? So you have this in the calculator. So let's say 5 minus 2 is 5 plus -2. Do you understand? So you consider subtraction as an operation that actually involves addition. Make sense? Because it's addition of a negative value. So that's what a polynomial is. So the question is e to the x a polynomial? Or any function satisfying this operation in general, this differential equation, could it possibly be a polynomial? Easy question, guys. Well, not necessarily easy, but at least you should have some reaction to it. Let me help you then again a little more. So Alexa says yes. Let me help you a little bit more, right? So for example, if I have 2 to the power of 5, right? I input 5. Can I carry out this calculation using only multiplication? Yes. And addition? I can carry out this operation. It's just 2 times 2 times 2 times 2 times 2. Yes? So the operation can be calculated only using multiplication here. Good? So it might appear to you that this is enough, that this is a polynomial. So there are two things. Notice that we have a set prescription. When we say a polynomial, it means that every input we plug in, we use the same operation types to calculate it. You understand? We don't vary our operations based on the input. That's the first observation here that we make, right? So for example, if I have 2 to the power of 3, that's 2 times 2 times 2. So if I say I can carry it using multiplication, I actually change the number of times I use multiplication. Remember, in a polynomial, you have the operations entirely fixed, right? So what is a polynomial? it's the same operation type, the same sequence of operations regardless of each input, right? So we have something like p of x equals to 3 minus 5x plus x squared. Notice that what I do to the input, if I change the input, the type of operations I carry and the number of multiplications and additions I carry stays the same. It's just I use the different input to carry out the operation. Does it make sense? So it's not only that I use only multiplication and addition, it's that I use for every input I use those operations the same number of times, right? So let's try to think of it, guys. Good? Are we ready? So first, the question is intelligible to you. Do you understand what I mean? If you think of it, right? So what can you carry out? You can carry out operations that are essentially polynomials, are what you truly understand. Maybe a slightly bigger class where you can change the number of addition and multiplications. But essentially, polynomials are the simplest functions. They are the first operations that you learn. So here. So I wrote several objections. So first of all, it's not obvious that e to the x is a polynomial because e to the power of 3 is e times e times e. That's wonderful. It just carries out multiplication. But what about e to the 1/2? That's just the root of e, right? And roots, well, I don't have, if it were just as simple as multiplication and addition, maybe you would have known what is root of 2, or at least how to carry out the calculation. Right? So if I told you to multiply 27 by 15, even if the operation were not so simple for you, you could do something, right? You could figure out what this answer is without a calculator, correct? So for example, what is 27 times 15? You can write it as 27 multiplied by parentheses 10 plus 5, right? And then you can just we have 270 plus 5 copies of 27. You can carry it out, good. You can carry out, in theory, any number multiplied by any other number, any number that you recognize, of course, right? When you multiply by root of 5, you haven't figured out what root of 5 is. You haven't figured a number for it. Good? Are you with me, guys? What I'm now trying to explain is very deep. It's very useful as well. Okay? Always ask yourself, how do machines carry out calculations? Machines only understand addition and multiplication, essentially addition, which you can then use to simulate multiplication. So, well, let's try to understand, right? So let's take a quadratic polynomial. Could e to the x be modeled by a quadratic polynomial? In other words, any input in x, let's say e to the 1/2 will be 1/2 evaluated somehow like this, right? Or e to the 5, it will be, you plug in 5 instead of the x and it carries out the calculation. Could it possibly be a quadratic polynomial? And again, what do we expect? We are talking about a function whose derivative is not altered. Do you understand? That's a very useful property. Now, what about polynomials? Do they suffer alterations when you carry out differentiation? Well, let's take the derivative once. Carry the derivative once, the constant a0 disappears. It becomes a1 plus 2a2 times x. Do you agree, guys? You remember we learned the shortcut because we can carry out partition or factoring of n powers, and we can carry out differentiation for x squared, x cubed, for any integer power of x. We already have a shortcut for evaluating the derivative. Do you remember the shortcut, guys? Right? Makes sense, right? So the derivative of, in general, the derivative of x to the power of n, where n is a positive integer. That's at least how we proved it, right? We proved it only for positive integers. Is n x to the n minus 1. Do you remember that? Good. So we have this derivative. Good. I see replies from what? From 3 people. The rest of you, what? Have you died? Are you alive? Over there in the boxes, guys. Oh my God, yes. It's so quick to show that you're still breathing. Don't disconnect, yes? All right. Don't allow de Blasio to take you from your oxygen. You take then another derivative, and what do you get? You get 2. I'm just reducing it completely, right? You might already say this is not the same as what I started with, but I'll take 3 derivatives, and I get 0. Do you agree? I end up constant. Taking derivative again and again and again, I reduce it to 0. What will happen if I take the derivative of a function that doesn't react to it, right? 2 derivatives, the function stays. 3 derivatives, the function stays. And it's not a constant function. Do you understand? So this function will not change after 3 derivatives, whereas polynomial of degree 2 will disappear to 0. That means that e to the x could not possibly be a polynomial of degree 2. You cannot possibly model e to the x with a polynomial of degree 2. Do you understand how I figured that out? Because I found a discrepancy. I found a difference between this type of function and e to the x, or any function whose derivative does not change the function. Yes? You with me, guys? It's called, like in Russian, you say, как с гуся вода, like water from a goose's feather. Derivatives don't affect the exponential function e to the x, but taking enough derivatives and a quadratic polynomial is annihilated to 0. All right, what about, could e to the x then equal to a cubic function, to a cubic polynomial? You see, I'm trying to, maybe if I add up terms, maybe I will be able to simulate e to the x. Could it possibly equal to a cubic polynomial? I wait for your replies. Right, and be very certain, right? So Steven says no with a question mark. Right, I want certainty, and certainty, not just full certainty, but certainty of a person that can explain. Right? Why cannot e to the x be exactly, Alexa? Right? Why not? Right? Why can't an exponential function e to the x be simulated with a cubic polynomial? In other words, be a cubic polynomial. What's the problem? Stephen, beautiful. After the 4th derivative, you see, you can find all sorts of discrepancies, but as soon as you find that something is true of e to the x, but not true of the degree 3 polynomial, you now know that they cannot be the same object. You understand? Because the same properties, the same features must hold for the two names, right? For if the cubic polynomial refers to the same object, the cubic polynomial has the same property as that object. Make sense? So here I carry out the different derivative. Do you see how I do it? I don't have to do by definition anymore. I have that's because I already did it. I already know how to take by definition the derivative of x to the 5 or x to the 7 or x to any positive integer n, so I can carry out the derivative. I carry it once. And you remember, we also have the laws for addition and laws for scalar multiplication. I hope that those were clear. So first derivative, it becomes a quadratic. Second derivative, it becomes linear. Third derivative, it's a constant. And then the fourth derivative, the derivative is identically 0. Yes? Polynomial of degree 3 disappears after 4 derivatives to 0. Whereas the original function, take derivative once, it's the same function. Take it again, it's the same function. After 4 derivatives, e to the x, if it exists, will stay the same function. So it cannot possibly be a cubic polynomial, right? Okay, well, how about a polynomial of some arbitrary large degree n? That, in other words, that allows me to, of course, make it smaller degree. You understand? I can make a n 0 and whatnot, right? Could e to the x be a polynomial of degree 1,000,000? So in general, could it be a polynomial of some finite degree n? You understand what I'm asking, right? You see how I'm able to solve this problem? I'm able to show that something is not true or impossible without actually carrying out calculations here. Now, why? So Christian is I think, one or maybe, I only see 2 people here. I don't know, guys. You don't like me. I don't look nice in the morning. You don't want to show me how disgusted you are by my appearance. I understand that. But, you know, mathematics is beautiful. You know, what's in me is beautiful still, right? So tell me, please, why do you not think that p to the x of some arbitrary degree cannot possibly be simulating e to the x, cannot actually be e to the x? Lakey, okay, a derivative of polynomial always returns something other than itself, which never satisfies the condition. That's very beautiful, Lakey. Yes, you are thinking mathematically. Good, right? What about the rest of you guys? You can say it possibly even in simpler form, right? How do you know it's never satisfied? So it's somewhat already is revealed. It n equal to e to the x because the polynomial does not equal its derivative. Zainab beautifully said. And maybe reduce it to absurdity. Understand? I mean, you say polynomial is not equal to its derivative. Well, the easiest way to argue that is to reduce it to absurdity. It's called reductio ad absurdum, I think. Okay, which means in particular, how do you know that? You see, a polynomial is not a constant function, correct? It's not a constant function because there is an x there. You can see that something is done, right? It's not supposed to be usually a constant function. If it's a polynomial of degree 5, it's not supposed to be a constant function. We can know that because limit as x goes to infinity will not be equal to a constant value. It will be going to plus or minus infinity. So guys, I do worry. I see 3 people or so that understand it. What about the rest of you? I can take this polynomial and I can take how many derivatives to make it disappear to 0. I can take how many derivatives if it's of degree n. If it were degree 2, I need to take 3 derivatives and it's gone. If it's degree 3, it's 4 derivatives. And if it's degree 4, it's 5 derivatives. And yes, correct, Huvang, I need to take n plus 1 derivatives, and the derivative, the n plus 1 derivative will end up being 0. But the derivative of e to the x never equals 0. Write in the comments yes if you understand, or something like that. I need to see how many of you are following. I did hear the correct answer from 3 people or 4, but what about the rest of you? You just don't like me, don't want to tell me the answer, or you don't understand? It would be not something difficult, correct? You could have figured it out yourself, guys, right? You didn't need me to tell you that. Just once you recognize somebody intimately, you know, if you recognize someone, if you have spent time with someone, you know their features, you know their quirks. So you know polynomial quirks from the perspective of differentiation is that derivative of a polynomial reduces its degree, and carry enough reductions of its degree and you get identically 0. Okay, so I just proved that that no finite polynomial can simulate what e to the x is doing. I underlined this word. That's what I proved, because notice that I truncated with finite degree. But you really, what if you really want to make e to the x a polynomial? In other words, you really like only using addition and multiplication, other operations you don't understand. What do you do? What's the leap of faith that you make? Any idea, guys? No? It's not an easy leap of faith. But here it is. If I, maybe you will complete my sentence. If I cannot make it a finite polynomial, in other words, one that terminates at some large degree, why not try? Take a guess. You don't want to take this leap of faith. You would have not survived. Oh, Alexa, yes, you would have survived, right? So you know what I'm talking about. Indiana Jones and the Holy Grail, right? You know there is this moment where you have to take a leap of faith, right? So that is the leap of faith that we are taking here, an infinite polynomial. You follow, guys? If I cannot hope to make it a finite polynomial because it will disappear, this is really important, right? Then why not imagine a polynomial that never terminates? You understand? So it will be going past the millionth degree, past the trillionth degree, it just goes on and on and on and on and on. Yes? Isn't it interesting what we're saying, guys? You see what happens here. So it's a constant plus constant times x plus a constant times x squared. It's infinitely long. Yes, not that it necessarily makes enormous sense right now, but that's what I mean by a leap of faith. You bring this creature into existence, you believe in it, and see if it will give you any useful true results. Good. So before we proceed with the argument, guys, I'd like you to recall what is the factorial, right? So this is not n, right? It's not n, it's just n factorial, which means it's if it's an integer, it's the product of this integer all the way to 1. All consecutive integers up to n, starting from 1. So for example, 3 factorial is 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. You understand, right? So, and by definition, 0 factorial is defined to be 1. There is the reason for that. If you're interested, we need to go to combinatorial analysis. I can give you a good reason, right? But you can take it for on face value. 0 factorial is defined to be 1. Okay? And so, again, what do I know about my function? The interesting thing about it is that I imagine that I found a function whose derivative equals to the function. Maybe it's e to the x is one of them, right? And at 0, it's equal to 1. You understand? Plug in 0, you get 1, and take any derivative of this function, and you get that function. Then the question is, how should I figure out what's my a0, a1, a2, all the way to an and onwards? Right? How do I figure those coefficients? I need to know the coefficients. If I claim it's a polynomial, an infinite polynomial, then how do I know what are the coefficients? Any idea? Look at it. How would I figure out a0? What's a very quick way to figure out a0? Can you guess? Look at it. I can plug any value into this function and there will be a calculation carried out. What do I plug in to figure out a0? Beautiful, Kirill. You see that, guys? Look at it. The complexity will vanish if I plug in 0. Do you see that? Because everything other than a0 will be decimated. A1 times 0 is 0. So everything is 0 except for a1. And I know what the function is at 0. We define it to be equal to 1. Yes? So plug in 0. Look at it. Here it is. Plug in 0. Everything past a0 disappears. And by definition, we said the function at 0 is equal to 1. So I have that a0 is equal to 1. I found my first coefficient. Now I want you to try to be clever. How do I make a very simple procedure to find the next coefficient, a1? I want to know what a1 equals to. Yes? Think about it, guys. Maybe you can figure it out, and then you are inventing mathematics. So Kirill already tells me what it is, but I want to see what the rest of you think, guys. Okay. More importantly, figure out. Well, how do I get to a1 now? I know that a0 is equal to 1. You got it? How I did it? I just know that if I plug 0 into the function, I get 1. Yes. But here is if I plug 0 into this infinite polynomial, only the constant term survives. How do I get to a1? That's good, Stephen, if you did, but why did you think that? What's a1? How do I find it? Finally. Finally. Yes, guys? Finally, because you finally gave me enough birthdays for me to run my scam. Christian Beam, take the derivative. Beautiful, Christian. Yes, somebody is reasoning, right? So what you can do, you want A1 to be in the same position as A0. You want to isolate it. And we don't even see, you have all sorts of formal critical objections. Can you do that? Can you take derivative of infinite things? What it means, but first you proceed by this this feeling that, well, it should make sense, right? What we are doing should make sense. We cannot make it finite, let's make it infinite. Let's see what happens. Let's hope derivatives work the same way as they do usually. We do, hopefully, guys. You do know how to take the derivative of x to the n. Yes? You understood that we use the definition. We have this factor of n powers, and we can carry it out. I even told you to listen to Oscar Wilde, right? To listen to that story. It should be very clear in your mind what it is. So we take the derivative. Here it is, guys. Look at it. I take the derivative, and here is what I get, correct? First of all, the derivative of my function is the function itself, because that's hypothesis. And if I take the derivative, the constant disappears. A1 is now the constant. And then we drop the 2, so it's 2A2. We drop the 3, it's 3A3, and onwards, yes? Now I plug in 0. I get that f of 0 is equal to f prime of 0. It's equal to A1, yes? And f of 0 is equal to 1. So A sub 1 is also equal to 1. Are you following me? So I was able to find two coefficients. Let's try to continue. What about A2? How do I find A2? Figure out A2. Can you see this, guys? So you understood the idea. Where is Alexa? You're there, Alexa, right? You figured out it's an infinite polynomial. So are you there, Alexa? Yes? Yeah, great. So you figure it's an infinite polynomial, you give it a shape, you begin creating it. Infinite polynomial, whoop, it appeared, it exists. It has some unknown coefficients, A0, A1, A2, A3 onwards. And now I'm trying to solve for those coefficients, because if I can actually make them definite, it convinces me of the existence more and more. So the question is, here I found A0 and I found A1. Everybody understood how I found A0 and A1? Did you understand, guys? Right? Yes, if you did not, all I did is very simply, I have a polynomial, everything else has an x, I plug 0, it annihilates whatever has an x. And only the constant term survives. And then to find A1, I realize I can take derivatives, and that will make the next coefficient the constant term. So then I can plug 0 again, yes? So now I want you to calculate what's A2. A2 now, yes? Today we finish at 12:15, correct? Yes, don't write yes to me just now, calculate A2. Beautiful, Kirill. And beautiful. Yes, so David on the right spot, Kirill exactly, Yuzu exactly. Yes, does it make sense, guys, what we do? We now have this expression, we take derivative, we always are going to take derivative again, so that we isolate a new coefficient. Are you with me, guys? Yes, David. Do you see the pattern, guys? So Joshua says he sees the pattern. What about the rest of you? Do you understand what's happening? I see, guys, I only see very few answers. So Alexa, so where are you lost, right? So you understand how it works. You just follow the stream where it takes you. You understand? So here, guys, let's look at the full procedure again. So starting is just understand what we're guided by, right? Very simple. So everyone here understands why I made the assumption it's an infinite polynomial, right? So it's just what I call wishful thinking. Very important thing is to know what to wish for. And in my personal experience, everything I ever wished for truly always came to be true, but I always ended up regretting it, you know, because everything has a price, or it comes through in a way that you don't imagine, right? Just an evil genie executes your desires, but not how they appear to you, but only a logical variation of them. So this function e to the x, or if it exists, or just any function that I'm studying, I'm trying to find a function whose derivative equals to the original function and whose value at 0 equals to 1. That's because I was considering the exponentials, and I know that the value of every exponential at 0 is 1. You understand? So I'm trying to see what sort of functions can I obtain. I then realized they cannot be finite polynomials, because this function, you take derivative, it doesn't change the function. Take derivative of any finite polynomial, and eventually the finite polynomial disappears to 0. Yes? So then I make this leap of faith. I assume that the polynomial is infinite. So there is no largest degree. You just go on and on like this. Yes? And then I ask myself, what are the coefficients? So I plug in 0. I know that f of 0 is 1. I am able to obtain a 1. Because I noticed that there are infinitely many a's. Yes, guys? Infinitely many a's, plug in 0. All the a's that have an x next to them are annihilated to 0. So I'm left with only one a0, and that's equal to 1. Yes? But then how do I figure out a1? To figure out a1, I realize if I take the derivative, it reduces the degree of x to 0, right? It always reduces the degree. 2 will be reduced to degree 1, right? 3 will be reduced to degree 2, right? So I take the derivative, the constant a0 disappears, and then what I have is a1 is by itself. a1 is here. You see it, guys? And then we have 2 times a2x, 3 times a3x squared, and onwards, right? And then if I plug 0, everything that has an x disappears, but a1 is now isolated. It has no x. So I get, look at it. On one hand, the derivative equals to the function. So when I take the derivative, it should be the same function. That's because that's the function that I'm searching for, yes? It should not change when I take derivative. And the function, when I plug in 0, look at it. The derivative equals to the function, so plug in 0, and you get 1. Yes? Plug in 0, you get 1. You're with me, guys? And that's how I know that a1 is equal to 1, because you have this expression, the derivative equals to, at 0 equals to 1, and a1 equals to 1. Entirely with me? You understand? I mean, it doesn't matter if I see a prime over f or not, because the function is the same when I take the derivative. The value of the prime at 0 is also 1. And the value of the prime is a1. So that means that a1 has to be equal to 1. Good? Now, I can continue with the same idea. I take, look at it. I want now to find a2. So I take one more derivative. Right, I take one more derivative, and what happens? The a1 is now gone, and I have 2a2, and then this is 3 times 2 times a3. Do you see? Because we drop an extra power, right? We had 3 dropped, and now we have 2 dropped, right? And onwards. And that's also equal to f of x. So then I plug in 0. Look at it. What do I have? I have 1 equal to 2 times a2. Because plug in 0, everything is annihilated other than 2 times a2. But no, now notice it's not a2 equal to 1, it's 1 equal to twice a2. So a2 is equal to 1 over 2. Are you with me? So tell me what would be a3? What would be a3 now? Can you do that faster? Right? So you see what's happening. Joshua, careful, not 1 over 3, because look at it. When I took more derivatives, look at it. What about the next terms? It's 3 times 2 times a3, because each time I take the derivative, I drop the power. Exactly, Zakia. It's 6. It's 1 over 6. You understand what happens? Look at it, guys. Here is second derivative. So when I take second derivative, I take the derivative. The 3 dropped in before. So now 2 will drop in. Yes? So a3 is 1 over 3 factorial. Why? Because look at it. Take derivative 3 times and plug 0. You get 3 times 2 times 1. Those are the powers that were dropped. They are dropped consecutively, because it used to be x cubed, then the 3 dropped, it was x squared, the 2 dropped, it was an x, the 1 dropped. You understand why we have 3 times 2 times 1? It's because we take 3 derivatives, and x to that power drops the powers 1 by 1. They are lower down. 3, 2, 1. So it would be 1 over 3 factorial. What would be a sub 4? Understand? I can mentally move in, everything else will have a 0. I can mentally move in the a sub 4 to be the constant. Yes? What would be a sub 4 equal to? Exactly who, right? You don't need the number, you can just give me the pattern. Pattern more important than the number. The a to the 4 is here. You see it here. I move it closer to the front by taking derivatives. And the function is not changed. Then I plug in 0, and I get the function at 0 is 1, right? So what happens? 4 drops. It's closer. It's now to the 3. Now 3 drops. Now 2 drops. Now 1 drops. And now we have 4 times 3 times 2 times 1 times a4. I plug in 0, I get 1. So, so I have 4 factorial times a sub 4 equal to 1. Yes, exactly. Right? Makes sense? You understand what I'm just saying, guys? So in general, I can figure out the nth term. The nth term is n factorial times a sub n. I just plug in 0, and I get that a sub n equals to 1 divided by n factorial. Yes? I figured out an arbitrary n. So here is my function. You see, this is the way you write infinite sum. This just means sum from the power of x equal to 0 to the power of x increasing forever to infinity. Mohammed, you didn't get how I did a sub 4. I just took 4 derivatives. So take we have a4 times x to the 4. Take one derivative, 4 drops. So it's 4 x sub 4 x cubed. Take another derivative. It's 4 times 3 times times a sub 4 times x squared. And you do that 4 times, you have all the powers drop 1 by 1. You understand? Every time you take the derivative, the power drops in, then the next power drops in. And the power is always 1 unit smaller. So you end up, to get to the constant, you end up dropping powers, the power 4, then the power 3, then the power 2, then the power of 1. That means the x is now to the power of 0. So that's when you have a constant term, right? That's how I get it in general. So that's a sub n. It's 1 over n factorial. Cool? I hope you understand it, guys. Right? So this is, I'm already introduced this notation somewhat. It becomes very important. This is unarbitrary. This is non-arbitrary. You see, this just means what? It means that it's the infinite polynomial just written in a compact, nice form. It means the powers go from 0 to infinity. In other words, they just increase forever. And then the first power is x to the 0, so it's 1. So it's 1 over 0 factorial, that will be 1. Then n is, let's say, equal to 1. So it's 1 over 1 factorial. Then n is equal to 2. It's 1 over 2 factorial, and onwards. You understand? So this captures this pattern. What this means, I hope you already understand this notation. N is a dummy variable. It's just indicating how the pattern is going, okay? So that means what? That means n is equal to 0, it's 1, then plus x, plus 1/2 x squared, plus 1/3, 1 over 3 factorial x cubed, plus 1 over 4 x to the power of 4, and onwards, forever. That's what this means. You understand? This first is x to the 0, then x to the 1, then x to the 2, and it tells you what to do with n. Good? You understand this notation, I hope. It's very useful and it's not arbitrary. And that should solve the equation, the derivative of this function equals to the function, and the value of the function at 0 is 1. Okay? So does it work? Let's see. First of all, if I plug in 0, all the x's annihilated, I get 1. So the function at 0 is equal to 1, correct? So it works. The first condition worked. Now let's try to take the derivative of this thing. Assuming, of course, you see, we haven't proved that that derivative of an infinite sum is the infinite sum of the derivatives. But we don't have to be that critical just yet. We are just first flight of the imagination. Then we make sure that we cannot possibly be wrong. So I take the derivative of that expression. You see, and I take it term by term. So what happens? The derivative of x is 1. The derivative of 1/2 x squared is 2 divided by 2x. The derivative of this term is 3 over 3 factorial x squared. Derivative of that is 4 over 4 factorial x, and onwards, right? It's forever, right? So what happens here? 2 over 2 is 1. 3 over 3 factorial is 1/2. 4 over 4 factorial is 1 over 3 factorial. I get the same function. Do you see? Because it's 1x, 1/2 x squared. It's the same function that I started with when I take the derivative. So I found some solution to my differential equation, right? Take the derivative of this function, it's the function itself. You've seen it? I just verified that based on the calculations, everything works. Good? Isn't it cool, guys? Isn't it cool? Now, we have a way to calculate e now, because e to the x is 1. This is what I'm claiming. E to the x is actually this infinite polynomial, 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed and onwards. So e, I just plug in 1 in here. E is 1 plus 1 plus 1/2 plus 1 over 3 factorial, blah, blah, blah. Remember, you see, because I believe that e exists, I now have a way to estimate what that number is. So for example, of course, I'm not going to add forever. I'm hoping that some finite addition, some part of the addition will give me a good approximation to the actual e. The actual e is the full sum, but the approximate e is let's say maybe I'll sum only 5 terms, right? Or 6 terms, right? So I have 1 plus 1 plus 1/2, blah, 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 and I get the approximation 2.71. You understand? If I add up to 1 over 5 factorial, I get the approximation 2.71. Remember, we claimed that there should be an e between 2 and 3. And here, without doing anything, I actually am getting an estimate of that number. Okay, let's try this for a moment with a calculator. 2.71, trying with a calculator, let's say doing that same procedure. Remember, it's derivative at 0. I plug in 0.001 minus 1 over 0.001 in the calculator, and the calculator gives me 0.997, pretty close to 1, correct? Now, if I decide to approximate e with one more term, let's say I add up the 1 over 6 factorial, right? So what is this number? It's 120 is 5 factorial. So I add up 1 over 6 factorial and I get approximately 2.718. When I do it with 2.718, this calculator game, I get a number even more like 1. Do you understand? Again, this is cheating because calculator, how am I knowing that what the calculator is doing? I'm just hoping that it gives you a sense that I was able, without doing any calculations, right? I mean, I knew that would be the answer. Without doing any calculations, I'm able to, because I believe a number like this exists, I'm actually able to give it shape, to make it real, to incorporate it, right? Because in other words, to give it body. You understand? Because I used this idea, infinite polynomial, and I was able to create a calculation. Isn't it cool? I believed maybe such a number exists, and if my belief is strong enough, and I know how to make mathematics answer, or make my wishes, my wishful thinking come true, I'm able to actually carry out the calculation just from belief. Okay, isn't it interesting? So I just was able to solve this equation. In general, this is known as Taylor series. And Taylor series is that if I know what is the value of the function and its derivatives at 0, all the derivatives, I hope to be able to represent it as an infinite polynomial. And it has this particular form. Okay, you can just play around with this game. It's a very, very useful idea. You can try in the physics book that I presented. Okay. And again, I want you to learn those ideas as fast as possible. They are extremely useful. They say when you do calculus, this type of thinking is what you do all the time. And so with all the problems that you're solving, I will show you some examples later on. So there is an optional section. The reason it's optional is to fully understand it, you need to know some combinatorial analysis, which I have notes on and which we can discuss if you decide to do it. Not that much. You need to know binomial theorem. Okay, so if you actually, well, here is what the optional section means. Here I assumed that this is my that this infinite polynomial is the exponential function, but maybe there are other solutions, right? I mean, I can say two things. I think, well, there is an exponential function whose derivative might be equal to 1, and this is, it seems like I obtained only one answer. So if there is one answer for the exponential function and there is one answer in general, they must be equal. But here I'm a bit more careful here. What I'm claiming is this. Suppose that here is the function we begin with, right? So we don't know anything that it's exponential or anything like that. This is the function we begin with. Then I prove it must be an exponential function. You understand? So this infinite polynomial must actually work like what I imagine exponential functions work. And actually it makes the exponential functions real. Because think about it, what is e? What is exponential number to the power of pi, or to the power of non-integer? What does it even mean? Okay, if I plug it into this function, it means something, because I can multiply, let's say, root of 5. I can multiply by itself many times. I can add it, you know, whatnot, right? So polynomial form makes it justified for everything. Okay, guys, so the lesson for today is over. Do stay for office hours to discuss questions if you have them. You should have been working other than in my class. You have reviews of limits and whatnot, right? You want to prepare for the, not just for the exam, but to know the material. Right? Just sitting through my lecture like this, you know, I know maybe 3 people follow. I'm not sure about what the rest of you are doing. And I do note which people stay. All right, I stop the recording now.